Alright, this will be a quick tutorial on how to determine chemical equivalence, which is going to be very important in nuclear magnetic resonance or NMR spectroscopy. So the question is, with 1,3-dichlorobenzene or meta-dichlorobenzene, how many chemically distinct protons are there in this molecule? And again, that will tell you how many signals you should expect to see in the proton NMR, right? If there are 18 different protons, there should be 18 different signals in the proton NMR. Clearly aren't 18 different protons here. There's only 4 protons, so let's draw them in. And so at first you might think a proton's a proton's a proton, but that's not quite true. Remember, the chemical shift in the proton NMR depends on the chemical or the electronic environment. So this proton that's kind of sitting between 2 electron withdrawing chlorines, you might expect to have a different chemical shift from this proton, which is farther away from them. We'll see if that's true later, but for right now, just try to figure out how many different ones there are. So I'm going to let you hit pause, and you might give this a shot even before we talk about it. Just hit pause and try to tell me how many of these protons are chemically different, and then come back. Okay. So the test you want to do, let's give these guys names. So starting here, we'll call that H alpha, HA, HB, HC, and HD. And so the test, you do it this way. So I'm going to replace HA with X, and that gets me this structure. Then I'm going to replace, so I want to test if HA is the same as HB. So then I'll replace HB with X. And that will get me this structure. All right. So I get 2 structures out of that. And then the question to ask yourself is, what's the relationship of the 2 structures you get? That is just barely on there, isn't it? So I'm going to draw up at the top. Well, actually, I don't have to draw any, I don't think. So if you look at these 2 structures, what is their relationship? Just assume X is some atom, some imaginary hypothetical atom. Are the 2 structures superimposable? Remember, if the 2 structures are superimposable, the 2 molecules are exactly the same. But they're not. If I flip this over, there's no way to arrange this so that they're superimposable in any way. The 2 structures, indeed, are constitutional isomers. Okay? If the 2 structures are constitutional isomers, think about the property of constitutional isomers. They're completely different. They boil different. They can have different solubility. They'll have different physiological effects. Basically, they're just different. And so that means HA and HB are different. So these 2, the technical term is non-equivalent. 2 non-equivalent protons in the proton NMR, they could coincidentally have the same chemical shift, but they probably won't. So these 2 signals, HA and HB, should both give different signals. Okay, does that make sense? Hit pause, let this digest a little bit. I'm now going to do some erasing. So we'll do another. We'll do another one. Let's test. Well, I should have kept it the same. Let's test HB and HC. Okay, so if you're back, we had HB already. I'll go ahead and draw that. Replace with the X. Okay, that's what you get if you replace HB with X. Now let's replace HC. Okay, again, these two structures are constitutional isomers. Constitutional isomers have different properties, therefore HB and HC will be non-equivalent. They'll give you different signals in the proton NMR. All right, let's keep HB there. Let's do HB again. And now let's do HD instead. So let's compare HB and HD. So let's draw what we get. Well, actually hit pause. Go away and draw what you'd get with HD. Replace HD with X, draw what you'd get, and see if you can determine the relationship of HB and HD. Okay, so here's what you get. So the top structure in black is what you get if you replace HB with X. The bottom structure is what you get if you replace HD with X. And look at that. If I take this molecule, flip it over, and spin it, these two are superimposable. You can also get that by nomenclature. If we number carbon 1 as having X, it goes 1, 2, 3, 4, so it would be 2,4-dichloro X benzene, and this would be 1, 2, 3, 4, 2,4-dichloro X benzene. They're identical. These two structures are identical. And so that means HB and HD are chemically equivalent. All right? If two protons, two carbons are chemically equivalent, they have to give exactly the same chemical shift in the NMR spectrum. So HB and HD will give one signal. And so if you work through this, there are actually the answer overall is there are three chemically distinct protons. So HA is different from HC, HA is different from HB, HC and HB are different, but HB and HD are the same. So A is one of chemically distinct, C is a second chemically distinct, and then HB and HD are also chemically distinct. All right, there's a tutorial. I'll give you a homework here in just a second.